All right, we are going to skip section 4.6, and the handout here is going to be our notes for section 4.7. We're going to talk about optimization problems, and this is really just another application of the derivative. In every single one of these problems, we're going to be either maximizing or minimizing a function, okay? So let's take a look at problem 1 here. It says that a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? Okay, so by then describing volume, it would indicate that I'm going to do something with volume of a box. Okay, the volume of any box is length times width times height. Now, this box has a square base, okay? So I'll let X represent the each side of the square base there, and H will represent the height of the box. Now, the manufacturer only has 108 square inches of material to work with. So how should the box be designed so that the volume is as big as it can possibly be? You know, should we have it more like longer top to bottom, or should it be more flattened? You know, still a square base, but how exactly should it look? Well, we're going to use a formula for volume of a box, which is length times width times height. Okay, or X times H would be just the general formula that I'm going to start off with here. And this is going to be a function of X. So I don't want X and H floating around. I'd like to have only X. Now, the surface area of this box is 108 square inches. Again, the box will be open at the top. So if I take the area of the square base and then add the area of the four faces wrapping around the box, I'm going to get 108 total square inches. Okay, or X squared would be the area of the square base. X times H would be the area of one of the faces on this box. I've got four faces there, so it's going to be 4XH. And like I said, when you add those together, you'll get 108 square inches then. Okay, now if I solve this equation for H, let's subtract X squared from both sides and then divide by 4X. Then I can know what H is in terms of X. So this formula for V, like I said, is going to be a function of X. Now where I see H, I'll go ahead and replace that with what I know in terms of X. That way everything is in terms of X. X squared over X is X. You could also split this into two fractions. That's what I've done. Now, one of the things that we'll want to do in working through these problems is we'll want to know the conditions on X, okay? So in this problem, what do we know about X? Well, we know X can't be a negative, right? We're talking about distance. That doesn't make any sense. I suppose that if X is 0, then you just have a line, okay? And the volume would be 0 since you haven't actually created a box in that particular case. If you just had a square flat piece of cardboard with a height of 0, and you've got 108 square inches of material to work with, then X squared equals 108 means that X would be plus or minus the square root of 108. I would disregard the negative since, again, X can't be a negative. Now that's the biggest possible value that X could be, is the square root of 108 inches. Okay, now I guess in that case, you wouldn't actually be forming a box. Again, so if you just have a flat piece of cardboard, the volume would be 0. Now, one of the things that I've done here, though, is I've got a closed interval, okay? And that's going to be a strategy that I would like us to try to do in these problems. We're not always going to be able to get a closed interval, but that's something that we should be at least attempting to do, okay? Because how these problems are going to go is after you've determined the function representing the situation, you're going to either maximize or minimize the function, meaning that you're going to want to find the absolute maximum point on the graph or absolute minimum point on the graph, depending on the situation of the problem. So I'd like to know the absolute maximum point on this graph on this closed interval. Well, the fact that I've got a continuous function on a closed interval, I'm guaranteed to have both an absolute max and an absolute min. That was the extreme value theorem, which was mentioned back in section 4.1. Okay, now I only care about the absolute max. But now in a situation where I can't get a closed interval, I would have to find the max or min point on the graph by using techniques from section 4.3. Okay, I'd have to, in other words, I'd first have to know that I've got a local max or local min, and then be able to prove that that is actually an absolute max or absolute min. All right, we'll look at some examples of that. So anyway, knowing that I've got a closed interval and a continuous function means that going forward in the problem, I'm going to be using the extreme value theorem, which is mentioned in section 4.1. Okay, now the extreme value theorem, if you were to flip back in your notes, was a guarantee that you would have both an absolute max and an absolute min on a closed interval, okay, for a continuous function. So how we find that is we have to find our critical numbers, and then we plug in those critical numbers along with the two endpoints on the closed interval, and we see which one is the biggest. Okay, so I'm going to do that. I'm going to find my critical numbers. Here's v prime of x is 27 minus 3/4 x squared. Set that equal to 0 and solve. Okay, if you add 3/4 x squared to both sides and then multiply by 4/3, then x squared would be equal to 36. Take the square root of both sides. X would be plus or minus 6. We've already said that x can't be a negative. So x is 6 would be my critical number there. Okay, now I'm going to plug in the critical number along with these two endpoints on the interval and see what's the biggest output. Well, okay, if I plug 6 into v, here's v, I end up getting 108, okay, if you were to check that. If we plug 0 into v, 0 minus 0 is 0. Okay, well that would make sense because if x is 0, you just have a line, you're not actually creating a box, so of course that volume would be 0. How about if we plug in the square root of 108? Well, if I plug it into this form here, the square root of 108 squared is 108. 108 minus 108 is 0. 0 times anything is 0. So the volume in that situation would be 0. That should make sense. You've got a flat piece of cardboard if the height is 0, and therefore the volume would be 0. You haven't actually created a box. Okay, now of course the biggest output was when x was 6. So that is a proof telling us that in order to maximize the volume of this box, we're going to want x to be 6 inches, and the height, if x is 6, would be 3 inches. Okay, 108 minus 36 divided by 24 would be 3. So the dimensions, 6 inches by 6 inches by 3 inches is what we'd want there. Okay, let's take a look at another problem here. A farmer has 180 yards of fencing and he wants to fence off a rectangular field that borders on a straight river. He needs no fence along the river. What dimensions of the field will produce the largest area? Okay, so he's going to build this rectangular fenced-in area along the river, and he doesn't need any fence along the river. He's just going to use the river itself as enclosure. How exactly should this look then to have the area be as large as it can possibly be? He's only got 180 yards of fencing to work with, so should he design this more, longer, like left to right? Okay, I'm just making up some numbers. Like if he goes with here's 15 yards by 150 yards, he gets an area of 2,250 square yards. Okay, so that's, I guess, one option you could go with. Or maybe he might want it more jetting out in the field type thing. Okay, like what if he goes with 80 yards by 20 yards? Well, the area of that rectangle would be 1,600 square yards, so he wouldn't want this option if he wants the biggest possible area, right? This number is bigger. Okay, in general, he's got a rectangle, and let me call the two sides jetting out in the field that are parallel x yards, and I'll call the remaining piece that is parallel to the river y yards. Now, we want to maximize the area. Okay, what is the biggest possible rectangle that could be built? We want to maximize the area. Area of a rectangle is length times width. Okay, now I'm going to create a function of x, and I'd like to have just x, not x and y, floating around. He has 180 yards of fencing to work with, so if I take x plus y, or 2x plus y, I get 180. Okay, and if we subtract 2x from both sides, then this remaining piece of fence, y, in terms of x, would be 180 minus 2x. Okay, in creating this function, a of x, it's going to be x times y, but where I see y, I'll go ahead and write 180 minus 2x. That way everything is in terms of x. Distribute x into those terms. And I want to state the conditions on x. So what do we know about x? Well, x can't be a negative. We're talking about distance. I suppose x could be 0. If x is 0, then the farmer is just going to lay fencing right along the edge of the river. He's not actually going to build a rectangle in that situation, so the area would be 0. But that's a possible value for x. And remember, I'm trying to get a closed interval here to avoid having to use a table like a first derivative test or a second derivative test. So x could be 0. Okay, now what if y is 0? If y is 0, then that means that he's going to lay fencing right out in the field and then wrap it right back, and he's not actually building a rectangle there, but x would be 90, right? 90 feet out, 90 feet back gives us 180 yards. 90 yards out, 90 yards back gives us 180 yards. That he's he's used all of that up now. So x can't be bigger than 90 yards. Okay. Now I've created this closed interval. I've got a continuous function, so the extreme value theorem gives me a guarantee that I will have an absolute max and an absolute min on this closed interval here. Now I care about the max, right? I'm maximizing the area, and so let's go ahead and find our critical numbers. We'll plug in the critical numbers along with the endpoints on this interval, and we'll see what is the maximum output there. Okay, a prime of x would be 180 minus 4x. Set that equal to 0. If you add 4x and divide by 4, 180 divided by 4 is 45. Okay, so if I plug 45, that's my only critical number, into the function a, here's a, I was getting 4,050 square yards. Okay, now if I plug 0 into a, here's 0 minus 0 is 0, and again that makes sense. If x is 0, the farmer's just laying fence right along the edge of the river, not actually building a rectangle, so of course the area would be 0 square yards. How about if x is 90? Well, if we plug that into this part here, 180 minus 180 is 0. 0 times anything is 0. So the area would be 0. That should make sense, right? He's not actually building a rectangle if he just goes 90 yards out and 90 yards back. Okay. Now the biggest output here was when x was 45 yards. So the dimensions that will produce the largest area would be 45 yards. If x is 45, y would be 90 yards. And that's the dimensions that he'd want to go with. Okay, if he goes with any other dimensions, here's some examples. The rectangle is not going to be as big as it could have been. Okay, he's going to get an area that is some number that is less than 4,050 square yards. Okay, of course that'd be a nice thing to know if he's designing this enclosed region. Hey, I've only got 180 yards of fencing to work with. Like, what is the biggest rectangle that I could make? Well, here's a way to figure that out.